Okay guys, this is the 5th video of 6 for reviewing for the semester exam. Okay, so this is dynamics. This is the second half of it. So let's look at this next problem. I'm on page 17. Okay, these are elevator problems, very important. Okay, my weight, if my mass is 60 kilograms, my weight's mg, which you know, 60 times 10, 600 newtons. The elevator has no acceleration, either standing still or moving at constant velocity. We know that the weight has to equal the normal force. So sketch a free body diagram for each of those. We know that F net would equal 0, acceleration therefore equals 0. What if the elevator's upward acceleration? Well, then the normal force has to be bigger than the weight. And F net would equal the bigger one, normal force minus weight. You should realize if the normal force is bigger, the scale is reading more than your actual weight. N is the scale reading in all cases. It only reads your weight if you're in equilibrium, like in this example right here. In this case, the scale is reading more than the weight. You're feeling smushed to the floor. The elevator has a downward acceleration up to, okay, because it's downward acceleration, the downward force of weight has to be bigger than the normal force. So the F net has to equal the weight minus the normal force. In this case, the scale will read less than what you weigh, and you feel lighter, like butterflies in your tummy. Okay, if the elevator is in free fall, that means the only force acting on you is your weight. If you're on a scale, it wouldn't read anything because the scale is falling with you with the elevator. It's not pushing up against you. In which of these cases are you in equilibrium? That's when F net is 0, when all the forces are balanced. There's only one case. Well, case 1, either standing, the elevator's at rest, or is moving with constant velocity up or down. Calculate the normal force acting on you in each of the cases above. Okay, so I'm solving for N. So it's easy right there. N equals the weight equals what I already did up here, 600 newtons. Okay, so let's do this one. Acceleration is 2 meters, so F net is ma. Your mass is 60. 60 times 2 is the net force, 120. Okay, so F net, 120, is equal to normal force minus the weight. The weight is 600. So N is equal to 120 plus 600 equals 720 newtons, much bigger than your weight. Okay, this one. So we had the same acceleration too, but it's downward. So I'm not going to do the work again. I got 120 like before equals, what was it? 600 minus N. So, and the normal force is going to equal 600 minus 120, which would be 480. Okay, which is less than your weight. In this case, n is equal to 0 because you're in free fall. The only force acting on you is your weight. Okay, for following scenarios, tell whether the same. Okay, this is good. This is all conceptual. Things need to keep on doing what they're doing. Object at rest remains at rest. Object in motion remains in motion unless acted upon by an outside force. Okay, so that's first law. When the road is covered with ice, cars tend to keep on going in a straight line rather than making the curve. Okay, object in motion remains in motion with constant velocity unless acted upon by an outside force. If you don't have friction keeping you around in a circle, you're going to keep on going in a straight line. So that's also the first law. Using aluminum steel makes it possible to trim force off. The less the weight of the car, the less fuel it takes to make it go. F net equals ma. If your mass is smaller, it takes less of a net force to give you the same acceleration. That's the second law. The rock hits you back. That's the reaction force. That's the third law. You hit a rock hard with your foot, it hits back with the same force. For every action, okay, that's the third law. Forces tend to accelerate while masses tend to, okay. That is the second law. That is the law of inertia, the first law. So it's a combination of 2, and 1. Boxers often because their brain slams into their skull. Okay, so this is kind of subtle. Ugh, I hate talking about this. But your brain stays when your face gets pushed back. So your brain is tending to remain at rest while your whole skull is moving backwards. So that really is the law of inertia, first law. Your brains tend to stay in rest unless acted upon a net force. Well, it's kind of loose in your head, so as you push the head forward, it smushes up. It can be separated and smush up against your front of your skull, causing concussion. Whiplash. Okay, same idea, but on your body. Your head, if it's not restrained by a headrest, we talked about that in class. That's the second law. That is the second law. Takes more force. Okay, F net equals ma. Second law. That's the third law. Action reaction. That's the first law. Okay, that's F net equals ma. Usually the guy with the smallest mass has the bigger acceleration if he applies a given net force. I don't know. Or you could say, I don't know. That could be 1 or 2. Because they're talking about fast speed accelerating to that speed and the mass. So that's why I think it's 2. When you're running through the woods, your toe is stopped by a root, you fall forward, not backwards. Well, your body remains in motion, even though your bottom part of your body stopped. So you fall, you trip. That's first law. Seatbelts are necessary in moving. Yeah. Or else you will fly through the windshield when your vehicle is suddenly stopped. So that's really the first law. When you step off a boat, off the dock, the boat moves away from the dock. Okay, so as you step off it, you push it away. The boat pushes you so you can get to the dock, but you push the boat away. So that's the third law. Okay, so let's finish off with circular motion. Actually, let's say that's the end of this 5th video, and we'll start the 6th video in a minute. That'll be the final one.